let's talk about screening for a disease or a condition or something like that. All right, so let's suppose that 10% of some population has benign chronic flatulence. Yes? Okay, so when do you multiply? When do you add? Okay, if you want probability of A union B and A intersect B is disjoint, they're mutually exclusive, then you can take P of A union B is P of A plus P of B. Okay, and that's one of the axioms, right? That's just got to be true. So if you're looking for the probability of a union and the events are disjoint, you can find that probability by adding. If you want probability of A intersect B and A and B are independent, you can find it by multiplying. P of AB is equal to P of A times P of B. And that's sort of the definition of independence. Okay. If you're looking for the probability of a union and the events aren't mutually exclusive, you can't just add. You got to subtract off the probability of the intersection. If you're looking for the probability of the intersection and the events aren't independent, you can't just multiply. You got to do something else. You could use the multiplication rule, because it's always the case that P of AB, it's always the case that P of AB is equal to P of A given B, P of B. Just in the special case of independence, P of A given B is P of A. Learning that B happened doesn't tell you anything about whether A happened. It's the same as the unconditional probability. Over here, it's always the case that P of A union B is equal to P of A plus P of B minus P of A intersect B. In the special case that their intersection is empty, that probability is 0. So it reduces to this. We good? Okay, people have had a chance to... Okay, so suppose we have a way of screening for benign chronic flatulence that has a 90% chance of correctly detecting that you have this condition, which is not fatal, and a 10% chance of a false positive. Okay, so there's a 10% chance that the dog did it or something. Okay, and you pick a person at random from the population, so everybody has the same chance of being picked, and you test the person, and the test reports positive. What's the chance the person actually has the disease? So I don't think I said out loud that we've got 10% of the population has the condition. The test is 90% accurate. Somebody tests positive. What's the chance they actually have the disease? Now, this is an invitation to make them. People's intuition very often leads them astray in this particular thing. Think, oh, if the screen is 90% accurate, then if somebody tests positive, there's a 90% chance they have the disease. Right? Wrong. Yep. What does the 90% say? It's 90% chance that you test positive if you have the disease, not 90% chance that you have the disease if you test positive. It's the other way around. Okay? So what we need to do is turn the conditional probability of testing positive given that you have the disease into the conditional probability that you have the disease given that you test positive. They're two different things, two different conditional probabilities. One is probability of A given B, the other is probability of B given A. Right? Okay, well let's use D to denote the event that the person has the disease, T to denote the event that the person tests positive. So translating the words into symbols is the hard part of most of these problems. Once you've got it translated into math, then the math isn't very difficult. Right, so what the problem statement said is that 10% of the population has the disease, so the probability that a person picked at random from the population has the disease is 10%. P of D is 10%. And the test has a 90% accuracy, is interpreted to mean the chance that you test positive given that you have the disease is 90%. The chance that you test positive if you don't have the disease is 10%. Those are two different pieces of information. You can't derive this from this, right? The numbers are happening to be the complement because we're saying that the test is sort of 90% accurate in both directions. The chance of a false positive is 10%. The chance of a false negative is 10%. Does that make sense? Okay. All right. So what we're supposed to find is what's the chance that the person has the disease given that they test positive. What we're given is what's the chance they test positive given they have the disease, the other way around. Okay? So by the definition of conditional probability, that is simply the chance that they have the disease and test positive divided by the chance that they test positive. Now, problems like this that start involving conditional probabilities, the easiest thing to do to solve them is to draw a tree. If you draw a tree, you will seldom go astray.